Good afternoon. We are the HAZMAT Safety and Reconnaissance Unit. My name is Sabri Caillouette. This is Dana Pico and Christian Palomo. So this is a little bit of our overview. Some of the new areas we'll be covering will be power supply, manufacturing, assembly, testing, prototype assembly, and along with the other areas of show. So the problem statement, there is an increase of chemical use, specifically in manufacturing, and this leads to a greater risk of hazmat issues and breaches. And so a little bit of a background is when there is a hazmat emergency or situation, hazmat certified firefighters are called to contaminate the scene, and some of the safety concerns and issues that they are facing is that they are only allowed in the scene a certain amount of the time. They don't know which chemicals they're exposed to sometimes. Sometimes they don't know what the actual scene is and don't have the right information. So there's a lot of risks associated with hazmat. So Chris will be covering benefits of the HRU.
All right, benefits of our system is, most importantly, it would eliminate risk involved for the firefighter that's entering the scene. One of the major issues that happens when a firefighter enters the scene is they have very limited information of what's going on in the actual scene. They have to see it for themselves. They can't go off just based off of someone else's word. Another thing it would help with the setup process. Once the firefighter arrives at the scene, they have to set up a barrier and get suited up depending on the type of material at hand. And this can take around 15 to 30 minutes at a time. So this would help that and facilitate the data gathering in the scene itself. As I mentioned before, they set up the perimeter, which in preparation can take around 30 minutes. And as well, they're also limited to the amount of exposure they can have depending on the suit and the contaminants at hand. So this will help limit that amount of time they need to be in contact with the contaminants. One of the big issues, one of the bigger obstacles that we hope to circumvent with this design is the stair climbing. One of the benefits that we have is we're using a tread, which will help for which has benefits, which is all-terrain and for very simple maintenance. However, it does lead to a little bit more complex design rather than a wheel, which is just kind of a bearing. But we feel that this design does have potential to climb and go downstairs. We'll talk about that later. Here's an example of just some of the sensors, as I mentioned, facilitate the data gathering. How is it being done? We're for the final design, it was to mount these sensors, these are actual sensors that are used from the HAZMAT firefighting department themselves. Mount them onto the robot using a sensory bay, and have cameras to be able to relay the information to a control center where a firefighter can record the information and get a feel for what the situation is at hand. Danny's going to talk about the design constraints of our system.
So the design constraints. For starters, mobility is the chief concern. HAZMAT firefighters, when they're going into the scene, they are already limited with their mobility because one, they are carrying heavy breathing apparatus equipment. On top of that, they have whatever tools they're taking in with them, which they may need. So the complexity of the problem is extremely manifold because it's not just about building an apparatus that can read and take measurements. It's about needing to get in there. For our project, realizing the complexity of the overall requirements, we decided to focus strictly on mobility. So there is not a sensory bay on this apparatus, nor are there appendages, but it does have a camera for piloting the apparatus, and it does have, as promised, a working suspension system, which is to assist with climbing various terrains, not just concrete and not just smooth surfaces. A real big design constraint, or a set of design constraints, comes from the NFPA, which is the National Fire Prevention Association. In particular, as you see here, actually the actual number wasn't listed, but I believe it is 1911. That set of standards is a couple pages long, and it deals with everything from the safety factors for the ladders on the fire engine to the helmets that the firefighters have to wear. And once again, for hazmat firefighters, there isn't a very huge difference in the equipment used, so the standards have to meet those, but then as far as chemical and vulnerability itself. So our proposed design, as mentioned, this is what we envision a full, working machine would look like, one that addresses all the aspects of the project. But if you're just going to address mobility, a power system, power supply, and a camera. So here you see we're comparing and contrasting between those two. Also, we have a render in here. On to prototype design. The frame is made entirely of 6061 aluminum. We chose aluminum instead of steel, which is a little more difficult, more costly to machine. And rather than using some exotic materials which would be lighter weight, we chose aluminum because for a one-off prototype, we want to see, does this even suggest that a larger scale apparatus will work? It's very adequate for this test. So here you see what the frame looks like before any of even the rotating assemblies or any of the auxiliary panels were installed. And here you see a suspension arm with the torsion springs shown, as well as some sprockets. For the motors, for our power system selection, or not a power system, for our motor selection, we used work energy theorem based on the height of the stair, to determine how much energy would be necessary to move a certain size vehicle up the flight of stairs, and we considered it for a continuous run, so that would be a worst case scenario. There are some buildings and some constructions where you may encounter multiple flights of stairs, and maybe even connected gantries. So it's quite feasible to think that you might be encountering more stairs than you would perhaps like. At this point, I'm going to hand it over to Chris, and he's going to discuss the electronic systems.
All right, just as Daniel said, the control system was not a main aspect or a focus of our design. However, it is important to operate and to test the robot. For this, we could have gone, we spoke before, we talked about Arduino and maybe Raspberry Pi. However, to simplify the control aspect of it, we went with a VEX system. Is a high school robotics kit, which was, for us, it was very easy to program. As you can see, a sample program, which is just to control the tank drive, and as well, it was cost effective for us because we were able to. We were allowed to borrow it. I'm sorry, we were allowed to borrow it and mitigate that cost, and as well that time that would take to program a Raspberry Pi or Arduino. Again, with electronics, the camera system, we have a little D-Link camera, which is an IP camera. It connects to a router, which then relays the video feed through a web interface. From that, we were just able to have basic control of the field of view and be able to test if this is a good placement for the camera. Obviously, this is not a very good camera for this operation. It has a low resolution, as well as just it's stationary. So future revisions were considered to have more array of cameras, to have higher quality cameras, and to have more control over the cameras. Well, to realize this is also a 35% scale model of the full design, not the actual full design. So more area will be granted for these kind of electronics. As for the power system, we decided, again with the budget in mind, we decided to go with steel lead acid batteries, which are most cost effective for us. However, we did consider other battery technologies such as nickel cad and as lithium iron phosphate, but which with exorbitant rates for those batteries, we decided to go with lead acid. Sorry, the lead acid batteries in a parallel configuration, which gives us about 16 amp hour theoretical capacity and an estimated runtime of 21 minutes. However, in testing, we were able to conclude a runtime of over an hour. And this is also due to a lower amperage draw, which we expected, which we calculated these off of a worst case scenario. And here you can see an example of the circuit diagram of which we use, which we tried to incorporate safety, which kill switch, and having most of the electronics connected by fuses to avoid any issues with the motors and this kind of encasement. Sam will talk to you more about the manufacturing.
So to continue manufacturing, we decided to take a couple different options. The first option was water jetting. So on the lower left-hand side, you're going to see the part file that we used to send to the water jet. All these dimensions and drawings are through cuts, so we didn't need to illustrate any features or send any models. And then we decided to CNC a lot of the other smaller features for the frame, as shown in the top left side, shown in the colors of which we were able to machine a Zipco machine shop. Then after we got the frame manufactured, we went ahead and fabricated the rest of the parts using the studio machine shop. And so as you can see on the right, machine shop facility and studio machine shop. So for the assembly, so just a brief overview of so for the frame we used basic hardware 1032, just for the availability and low-cost tooling in order to use that hardware. And then for the gear system, we use shafts that we bought at a surplus metal shop. And then for the tread system, we use rivets to fasten to the chain tabs in order for it to give it a secure fitting joint. We use that instead of hardware just because to prevent protruding, and so that it's compact and it's very feasible to manufacture and assemble multiple holes along the tread. So you'll see those photos on the corresponding figures. And then also Velcro for the electrical components, just because it's removable. That's easy to conform to the electrical components, so I figured that would be the best option. And then to introduce the testing, so we did stair climbing, a battery discharge test, speed test, and following the other tests, which Dan will.
All right, so first up in our test was the ultimate goal, the one that we really, really wanted to get, and we missed it by that much. Stair climbing. It's a bit of a balancing act. Our initial tests with the stairs showed that our power system calculations were on the money. There was definitely enough torque, but what we saw was a lot of the robot and the apparatus trying to roll backwards on itself once it reached a pivotal point. After doing a post-analysis of what is going on, we realized that the torque of the motors was basically acting to apply the torque in the opposite direction, not just trying to bear down. As a result, that was causing it to flip. We're thinking in further iterations of this size apparatus, just to master the stair climb, it would be ideal to keep it this size and keep playing around with that. We definitely think that research into tread technology is going to be important. The treads that were used here are actually it's actually a cut-up timing belt, and this particular type is made of neoprene reinforced with nylon. So it's actually a pretty sturdy material, but it's not necessarily very grippy. And we also noticed over time a very high collection of dust, constantly having to clean it off, and it still wasn't providing adequate grip. So we believe further research into that will assist in the future. Also, weight distribution could help. We experimented, as you see here in this picture, by fastening weights to the very nose of the apparatus to see if that would apply more torque in the opposite direction. Here you're seeing with 15 pounds. It does manage to climb with 15 pounds, but it does so at such a slow rate that, quite frankly, we found it unacceptable. And we believe that maybe weight distribution or redistribution is in order, so further areas of study. Now, some areas of success and actually some very good strong points. Pushing and pulling, overall, the apparatus is very strong, and it showed that it could pull a little over 125% its weight. To put that in perspective, it's a 47, almost 48 pound apparatus, this little guy, and it's not even the full scale one. And here in the picture, we were able to drag approximately 60 pounds. So I was able to do this on damp concrete with some moss and some leaves. So very, very terrain. Nothing that is laboratory or like a perfect scenario. Definitely a worst case. We also ran it through its paces on rock, gravel, grass, and we also took it over some other, here you can see some smaller steps where the torque was causing less of the motors, that is. The torque of the motors is causing less of a defect. It could actually climb quite well, we discovered, over some other obstacles, and at the end we'll get to see a video of some of that testing. At this point, I'm going to hand it over to Chris, and he's going to cover the survey of the standards.
Really quickly, some of the related standards that were involved with this, as mentioned before, the NFPA, which guided our factor of safety for a lot of our, for the design of the frame, as well as we took into account some of the OSHA standards. In this case, OSHA standard for 1926.65, which deals with hazmat scenarios and hazmat scenarios. It's a list of different definitions and different protocols that are involved with these kind of situations. As for our geo component, we try to make a design to be universally accepted. We took it to the highest criteria of building standards that we found. So the width of the stairway and some doorways and hallways, we found the stringent to be 36 inches. And we tried to conform our size. We have a width of about 10.5, which when scaled up to the full scale is within that reach, within that limits. And as well, we created a universal manual and so on. And for our conclusion, Daniel reiterating some of the numbers.
Okay, so here is the. Okay, so all the different testing that we did. We conducted a speed test to see how rapidly the apparatus can move across the surface. We calculated basically a maximum distance travel. This is based on the battery testing, which you see down here, the battery life. Battery life was simply a stopwatch running while we did the testing, and since there was still juice left, we ran it until it ran dry. We ended up with an hour and some change, 6 to 10 minutes. We tried to repeat the process again, and we repeated about the same, an hour and 5 minutes. So definitely it's within that 1 hour margin, which is good, even for this size apparatus. Here you see the weight, the maximum load that we would suggest that it pull under any circumstance, because this was a worst case. This would be what you would call a safe margin. Stair climb was not achieved. However, with further research, we believe that it is obtainable, especially with this platform, and from that, perhaps a lot of experience could be drawn from that and used to build a next scaled-up prototype and do further testing on the real station. Also, the maximum distance. Maximum distance, is, as mentioned before, is based on the traveling. This number, the required number, it comes also from the NFPA as well. There's also standards for HAZMAT to set up what is their operational zones, the hot zone, the warm zone, and et cetera, for operating safely. So based on that, 1,000 feet would be a trip in and a trip out of all the way from the warm zone into the hot zone where all the action is at. So at this point, I'd like to thank you for your time, take any questions, and go ahead and enjoy this video we put together of some of the testing.
Tell us what we were watching.
Okay, so here's an example of the uneven obstacles. We took this around backyard where we had a lot of rocky area and a lot of tree branches. Here you can see the testing where we simulated the weight loading. Well, we weighed that, it was approximately 61 pounds. We tried to increase the weight with some of the weights that you saw when we were doing the stair climbing testing, and we found that was pretty much about the maximum it can handle. And here's some more just different all-terrain testing that we tried to see, and you can see one coming up. It has a stair-like obstacle where it overcomes it pretty easily, which, as we mentioned, we feel that this does have potential for the stair climbing. However, it needs a little bit more research into the tread and to the weight distribution of the robot. But this is pretty much it. And then this video is on loop, in case you guys missed something.
All right, so you guys said that pretty much the main purpose for this robot is to avoid putting humans in harm's way in chemically dangerous situations. What went into your choices of materials, how you're going to encase it, etc., to make sure that this is capable of doing its job?
We noted that that material selection is very important. We didn't do specific research onto the types of material. We did some research, with decontamination, because we talked to some of the firefighters themselves and they talked to us. It's not about having something that's not being able to contaminate it, but it's something that is decontaminatable by different processes, such as just washing it with water, or by sending to a separate company that does that procedure. As we mentioned before, in this case, we focused mainly on the drivetrain and the mobility of it. We did those considerations are in mind. We did look into some different coatings. However, ultimately we were left at a brick wall, where some of that information we just couldn't get access to. And so further research, maybe in collaboration with a decontamination company, would help out with coming up with those materials.
I only ask because pretty much any lab you go into, whether it's even here, I'm sure, has an MSDS folder that contains all the relevant chemical information for any hazardous materials stored or utilized. And so to do a survey of that, to get an idea for yourself as to what it may be driving into potentially. So
Yeah, that's true. Even the HAZMAT firefighters we spoke, they mentioned the MSDS because that's actually their handbook that they have there. That's like their, that's their
chemical
machinery's handbook, basically. That's their Bible. So they get on a scene, we've got these present. All right, we got to break out these suits. We have to do this, X, Y, Z. Aluminum. The reason for the aluminum, on top of the fact that it is a cost saver, it was originally selected because for the larger scale prototype, it would represent a reduced weight overall in the frame, and also it's very workable, modifiable for developing into the full prototype. But along the lines of chemical safety, aluminum can actually undergo a variety of processes and coatings which could make it a lot easier to decontaminate. So we figured it was our best choice.
I think my biggest concern for you guys would be your tread.
Yes.
So
Some nitrates, some nitrates will eat right through the aluminum.
well, not only aluminum, but any rubberized
Right, too.
materials,
That too.
acids, strong acids.